Okay, so today is our May membership meeting, and I'm very happy to introduce our guest speaker, Gary Kader. Gary Kader works at Baldwin Wallace University, teaching several subjects, and he also runs the observatory at Burrell Observatory, which has a 13-inch refractor. And Gary's going to talk today to us about cosmic distance ladder, tell us how to measure distances out in space, out to the edge of the observable universe. So let's have a hand for Gary Kader.
So this whole thing is really easy. All we got to do is hand you a tape measure and say go. That's right. Done. Okay, thank you all. Y'all know it doesn't work that way, okay? So measuring distance in the universe is really fundamental to us, as far as what we're trying to do here. I mean, without the knowledge of distance and stuff, it really makes it tough to figure out what's going on with the various objects that we're looking at. And so, especially when it comes to the universe and figuring out, the expansion rate and that sort of thing, and we'll talk about all of those things, okay? So, some background. We use various methods to do this, okay? And giving someone a tape and starting walking is not one of them, okay? Except for measuring things on the ground, maybe, all right? So collectively, these various steps, because one depends on the other, as you will see, it's referred to as the cosmic distance ladder. So the greater the distance you're measuring, the more steps. Now we do have some real direct methods for measuring big distances. And so we'll talk about that a little bit with type 1a supernova and that sort of thing. So this is the various things we're looking at. Close by stuff we can do with parallax, which I'll talk about a little bit. You can also do spectroscopic parallax. That's the way we measure the distances to the stars before we send up satellites. We'll talk about those a little bit. And then Cepheid variables. That became very important to measuring distances to galaxies. And then the Tully-Fisher phenomenon. That's a very accurate way to measure distances to galaxies. And then we'll also talk about type 1a supernova, which is the kind of the ultimate way to measure distances. So, first rung on the ladder is parallax, but there's a lot of things we got to do before we get there. Okay? Parallax uses the size of the Earth's orbit. And so to figure out the size of the Earth's orbit, we need to figure out the size of the Earth. So this is going to, drill down a little bit. And we also need to be able to calculate the relative distances to the other planets. In fact, Copernicus was the first one to do that. He didn't get absolute distances, but he got relative distances. Once we know that, then we can start working out the actual distance from the sun to the Earth, which is called an astronomical unit. So, in order to get the actual distances, we need the diameter of the Earth. So, before we can determine the diameter of the Earth, okay, we need to determine its shape. Now, you've all heard that everybody thought the Earth was flat, okay? We've known the Earth was round since the 3rd century BCE, okay? In fact, Aristotle made a very good argument for all of that. If you looked at a lunar eclipse and they understood the juxtaposition of the sun and the Earth and the moon, and they knew that that was the Earth's shadow on the moon. And so no matter when we had a lunar eclipse, it was always an arc, so that you could deduce that the Earth was round. Also, he knew that there were stars that were visible in Egypt that weren't visible in Greece. As you went down south, the stars started coming up. So this, again, has to be round. So that wasn't the argument. In 1492, the argument wasn't whether or not the Earth was round. Anybody that was educated knew that. It was a whole distance thing, and if you're a sailor, if you're going to sail someplace, you want to get back, and you got to know how the winds work. So that was the whole argument there. All right, so Aristotle also argued that the moon was a sphere because the terminator was always this elliptic arc, okay? So he knew that the moon was round also. So obviously, why not the Earth? He was also able to calculate the relative distance from the Earth to the Moon in terms of Earth radii. Again, this is a relative distance. He couldn't get the actual mileage or whatever, but he could get the relative distance. And this was pretty clever, the way he deduced this. All right, the actual distance varies between 57 and 63 Earth radii, and he came up with 69, which isn't bad for the 3rd century BCE. And so he assumed that the shadow of the Earth out there was two Earth radii, or the diameter of the Earth, which is pretty close, but it was actually about 70% of that because it is tapered. He knew the longest eclipse was about 3 hours long, as best that they could measure time at that point. So we've got a lot of variables here. So it turns out you can figure out how fast the moon is moving because you know this is 2 radii and it takes 3 hours. So you take 2 Earth radii divided by 3 hours, you can get a velocity, you can get a speed, at least in terms of Earth radii. And that's what this formula here is all about. Also, you can get a formula for that by looking at a sidereal month. So 2 pi d, okay, which is this distance from the Earth to the moon, 2 pi d is the circumference of the moon's orbit, and if you divide that by 1 sidereal month, which is 27.3 days, you can get a velocity, how fast the moon is going. And so you all know from your high school algebra you have 2 unknowns and 2 equations. And so you can put these 2 together and you can get a ratio of the Earth's radius to the lunar distance. And he did all this in, 2nd century BC, which is kind of cool. I mean, he came out pretty close. I mean, it's not bad. Aristarchus was actually able to figure out, again, the relative distance. Well, he didn't do a good job of it, as you'll see, but anyway, the relative distance of the moon to the sun. In other words, how many lunar distances is the sun away? Again, not an absolute number, couldn't get it in miles, or stadii, which is what the measurement of the day was. And he realized that the first quarter moon, when it's exactly half, it's not 90 degrees from the sun. It's just off just a little bit. It would be 90 degrees if the sun was an infinite distance away, but of course it's not. So you have this little bit of an angle here. So trigonometry alert, there's going to be several of these, so don't panic. All right. So when the moon is exactly half full, there's a 90-degree angle between the sun and the moon. And so if you can measure this angle, then you can figure out this ratio. And x over y is called the sine. If any of you have never had trig, okay, regardless of how big this triangle is, for a given angle here, 87 degrees, that ratio is going to be exactly the same, whether it's a small tick on the table here or it's halfway across the universe. So that ratio, so that's called sine. You're going to get into cosine and tangent here in a little bit. So you're all going to you're going to know enough trigonometry when we're down here to be dangerous. Okay? So, turns out that the relative distance, he calculated that the sun was 19 times further from the Earth than the moon was. And he came up with 87 degrees. The real number is 89.8, which doesn't seem like it's very far off, but because of the nature of the cosine function, he was off by a factor of 20. Okay? So he was really far off. But that wasn't because his measurement was that far off, it was because the sine, the cosine of the angle. Any of you that ever had calculus, you're very close to 90 degrees, which is the inflection point, and so the first derivative is maximum. Okay, I just messed everybody up. All right, so no problem. All right, so in the 3rd century BCE, all this stuff was done by the Greeks, Eratosthenes figured out the diameter of the Earth. You've probably heard this story. he lived in Alexandria, which is at the mouth of the Nile River, and he heard that there was this well in Syene, which was south of him, that on the summer solstice, the sun would shine directly down that well and illuminate the water in the bottom of the well. That meant that the sun had to be directly overhead. And he knew that never happened in Alexandria, so he figured he could exploit that information to figure out how big the Earth was. So, he placed a post vertically in the ground, and at noon of the summer solstice, he measured the angle of the shadow. Okay, now he took the assumption that the sun was far enough away that the light rays were essentially parallel. And for the distances we're talking here, it's a pretty good assumption. Not a big deal. So he measured 7.2 degrees. And this is what it looked like graphically. You have the well in Syene with the light shining down the bottom of the well. Here's his post in Alexandria, and he measured 7.2 degrees. And if you remember geometry from high school, parallel lines cut by a transversal, all their interior angles are equal. So this angle here is 7.2 degrees also. So that sets up a very simple ratio. The circumference of the Earth is to this distance as 360 degrees is to that angle. It's a very easy ratio. So he knows what the angle is. He could figure out the distance to Syene. Okay? Turns out the distance to Syene was 5,000 stadia. That was the measurement of the day. That was the big measurement of the day. And so you plug everything in, and you get 250,000 stadia, which is pretty close to the real number if a stadia is about 1/6 of a kilometer. He came within about 10%. This is a fun little experiment to do on your own if you want to. I actually have in fact, I brought just one copy of it, but this is an exercise sheet for my students to figure out the size of the Earth. This is kind of cool. If you've got some kids that want to do something like this, you take a protractor, put a string through the little hole there, and with a weight, tape a straw on the end of it, sight the North Star through there, and read the angle. Just pinch it off and read the angle. And take a number of measurements. I tell everybody, take about 10 of them, and you take your 4 closest ones, and you take an average, and it turns out that there is a Cleveland, Florida, which is about 1,000 miles due south of us. And if you took that measurement there, you'd get 63 degrees. And so that can act as your well in Syene, and if you take the difference between those two, divide it by 360, multiply it by 1,000, you will get the diameter of the circumference of the Earth. And it's amazing, with that little piece of equipment, almost all my students get less than a 10% error. It's absolutely phenomenal. Most of them get like 5%, 2% errors, that sort of thing. So it's a neat little experiment. I do have a copy of that I'll leave up here if somebody wants it. I don't know if any of you are school teachers at all, but this would be a cool little experiment to do with some high school students or whatever. Okay. So he was able to get the circumference of the Earth. So that's one of the first measurements that we had, which is an actual, not relative, distance. So Copernicus was able to measure the relative distances to the planets, which is what we need to figure out what the actual distance from the sun to the Earth is. We're going to get to parallax eventually, folks, here. And so let me just remind everybody, these are planetary observing terms. You've got greatest elongation for the inner planets, which I think you're all familiar with, and you have opposition for the outer planets. There's one more for the outer planets. It's called quadrature. And it doesn't show up on this chart, but I'll show it to you in a minute. Well, measuring the relative distance to an inner planet is really simple, because when that planet is at its greatest elongation, its furthest distance from the sun angularly, your line of sight is tangent to the curve. And so that means you've got a 90-degree angle here. Yay, more trade. Okay? So it turns out that the distance to Venus is 1 astronomical unit times the sine of that angle. So, yeah, the sine of that angle is going to be this divided by that. Okay? So, again, we have a relative distance. We don't have the actual yet. Doing the outer planets, a little more complicated, but it is pretty straightforward. You have a position of apposition here, and at some point, the Earth is going to be, or the planet is going to be 90 degrees from the sun. So, just right at sunset, it's going to be right over here. And that position is called quadrature. And we know how long it took us to get from opposition to quadrature. What part of a year, whether it's 30% of a year or 40% of a year, whatever, how long it took us to get to quadrature. And so we know the period of the Earth in years, so we can use that as 1. That makes the math real easy. And we can figure out the planet's sidereal period. That's pretty easy because you can go by consecutive oppositions. I didn't go through that calculation here, but just assume that's very easy to calculate. And so turns out that this angle alpha that you see right here is the time it took to get from here to here times 360 divided by the period of the Earth in years. If we do everything in years, this makes it pretty easy. So that gives you that angle. Beta is the exact same way. It's the period, how long it took us to get to this position in years, times 360 divided by the period of the planet in years. And so that tells us that this angle here is alpha minus beta. You didn't know this was going to be a math lesson, did you?
No.
Okay. I'm glad everybody's not running out, but you're all astronomers, so you should be used to this. Okay? So there it is. The distance to the outer planet is 1 astronomical unit divided by the cosine of alpha minus beta. Again, a relative distance. We don't have an absolute yet. Now we got to get some absolutes. To measure the Earth's orbit, we need originally it was done using the transit of Venus. And once we've used the transit of Venus, we can use parallax to figure out what the distance is to Venus. And once we know what the relative distance is from the Earth to the Venus and Venus to the Sun, we can calculate our distance to the Sun. So this takes a lot of steps, but it all works. So if you go from 2 different points on the Earth and you look at the transit of Venus, it's going to transit in different positions. And by timing that, you can calculate what that angle is between those 2. I won't go through that. You guys want to get out of here sometime, right?
Yeah.
And I've given you enough math, all right, to scare you. So you can calculate that angle. And then you can calculate that distance to Venus, and you already know the ratio of the Earth's distance to the Sun and Venus's distances to the Sun, and so you can calculate the Earth's distance to the Sun.
Yes.
Yay, done. All right, now this is tough to do, okay? But transits of Venus only occur every 108 years, so it makes it kind of tough. But today we use radar ranging. That's how we got the actual distances, is to bounce radar waves off of Venus, and when you got the echo back, you can figure it out. What complicates it, of course, is that the Earth's orbit is elliptical, and so is Venus's orbit. So this whole thing is, gets a little more complicated than what I'm, showing you here. For the outer planets, you can use stellar occultations. This was a huge thing. I don't know if many of you really go out and look at stellar occultations anymore, but that was a huge thing in the 50s and the 60s. When I was getting Sky and Telescope magazine, they would always show you these occultations, and they wanted people to go out and time them. Because if you time how long a planet takes to go across, you're getting that same chord. And depending on where you are on Earth, you're getting different chords. And so you can then calculate the distance, say to Jupiter or whatever, based on that, the time it takes it to go across. So once we've calculated the distance from the Earth to the Sun, we've given that term an astronomical unit. You're probably all aware of that. Really good measurement for measuring things around the solar system. Not so much for any other distances, but it works well. And an astronomical unit is the semi-major axis. You got a major axis and a minor axis for an orbit. And so if you take the semi-major axis, it's really, really close to the average distance. So that's what they're giving you if you look at any book or anything. They give you the semi-major axis. Okay. So now once we get a reasonable number for the semi-major axis or an astronomical unit, we can start utilizing that to figure out how far the stars are, albeit within limits. Remember, any error you had in measuring the Earth's circumference gets multiplied when so all these errors get multiplied as you go along. So we're going to talk about parallax. And a lot of you probably are real familiar with parallax. If you hold your finger or a pencil up in front of your face and open and close your eyes alternately, your finger or your pencil will move back and forth. And that's because you're looking at it from two different vantage points. We're quite good at this, by the way. That's how we judge distances. That's why you can catch a ball. That's why you don't run into the guy in front of you. Okay? Your ancestors that were not good at this, okay, are not your ancestors, because they reached out for that branch in the tree and they missed it, okay, and they wound up tiger fruit on the bottom of the jungle floor. So we're pretty good at this, all right? And so how accurate this is depends on the baseline, and the baseline of our eyes is way too small to see anything in the stars. Stars are way too far away. So what we do is we use the orbit of the Earth. And if we look at a star, say in July, it'll appear there relative to the background stars. And if we look 6 months later, it's going to have moved a little bit. And we can assume that these background stars are so far away they're not really affected by parallax, although you can do some messing around and correct for that. And so, look at what we have here. We have another 90-degree triangle, okay? And so, using trig, we can figure out that distance. And so what you have is you have this parallax angle, how much that star has moved, okay? You got the baseline, which is the radius of the Earth's orbit, and that's the distance to the star. And it turns out that the tangent, another trigonomic function, it's not, when you see that on a calculator, it has nothing to do with a tanning booth, okay? It has everything to do with trig, is the baseline divided by the distance to the star. And so again, for any given angle, that ratio is the same regardless of how big the triangle is. So you can calculate the distance, which is the baseline divided by the tangent of the angle. That's where the term parsec came from. You've probably heard things quoted in parsecs, differences. That stands for parallax arc second. And that's how far a star has to be to give you 1 arc second of parallax. And that's about 3.26 light years. Now, since the atmosphere really limits our ability to measure these very, very small angles, we're probably only good for about 5 parsecs out, or about a little over 15 light years. That only gave us about 55 stars we knew the distances to very well. Okay, so that's not a statistically significant sample when you figure there's 200 billion stars in the galaxy. Okay, this is like talking to one person and deciding who's going to win the presidential election, okay? And being sure about it, right? That ain't going to happen. So one of our first big attempts at doing this with satellites was in 1989, and we sent out Hipparchus, and Hipparchus measured the distance to 120,000 stars, to much more accuracy and much more precision than we could here on Earth. That wasn't good enough for us, and so in 2013, this was a European Space Agency satellite, they sent out Gaia. And it was going to measure 1 billion stars down to about 20th magnitude, to an accuracy much better than Hipparchus.
What's the distance on that? How far out?
What? I have no idea. Okay. I do believe it's in orbit. I don't think it's at one of the L2 positions, right?
I meant how far using parallax could you measure to?
Oh, about 5 parsecs.
No, with this.
Oh, with this, we can get to 20%. We can get almost all the stars that are visible. In fact, some of them are actually too close to use this. Things like Betelgeuse is actually so large that you can't get a distance because you don't know exactly where you're measuring it across the, across the.
Because you actually see
core.
a disk with some telescopes.
What's that?
You actually see a disk with some
Right.
telescopes rather than a pinpoint.
Right. So, anyway, 40 times more precise than Hipparchus. It was activated in 2014. Last observations were actually, done in March 2025 or January 2025, and it was totally decommissioned in March of this year, so just a couple of months ago. But what's really cool is somebody took and plotted the data, and this is what you get. This is not a photograph. This is the plot of positions of individual stars from the Hipparchus satellite. Really cool stuff. So there's a lot of data here. Well, before we did spacecraft, one of the ways we would do it is using the HR diagram. I don't know if, did I give a talk on the HR diagram, I think?
I think so.
Yeah, anyway, you can actually use the HR diagram to figure out how far a star is away. If you know a star's temperature and that it's on the main sequence, and you can tell by the spectrum and the hydrogen lines and all that other stuff that it's on the main sequence, you know its luminosity. Because if you know its temperature, then its luminosity is going to be over here. And the luminosity is how much light the star is actually giving off. Think about it as the wattage on the light bulb. Okay? It's not how bright the star is. Bright depends on how we see it. So something that's close appears very bright. Something that's far away doesn't appear so bright. But this actually gives you the luminosity, which gives you the wattage on the light bulb. So if you know the luminosity, you can measure the brightness and you can figure out the distance. It's called spectroscopic parallax. There's the formula if you need it, okay? And so that's the way we did it until we sent up these satellites. Now measuring distances to the galaxies is a whole different kettle of fish here. And in fact, there were huge arguments in the 1920s about how far away these smudges people were seeing. In fact, Heber Curtis, oh God, I should have made a slide on this, but there was a great debate in 1920s at the Smithsonian Museum between Heber Curtis and Harlow Shapley about this. Heber Curtis said, the Milky Way is the entire universe. Harlow Shapley said, oh no, all these little smudges, they are other galaxies way, way far away. Heber Curtis won the debate, even though he was wrong. And I always like to point out to my students as to one of the things I really like in science is that arguments in science are resolved by the observations and not by the strength of the rhetoric. Okay? And so that got resolved by Edwin Hubble, and we'll talk about him in a little bit. So if we know the luminosity of an object, as I told you, we can figure out its distance. Enter Henrietta Leavitt, one of my heroes. I don't know if you remember, I think I did this talk about 5 or 6 years ago on the Harvard computers. She was one of the Harvard computers, which is this whole group of women that were analyzing photographs in the late 1800s, early 1900s. And Henrietta Leavitt's thing was variable stars. And so there's a star in a period's history when they're unstable. I like to tell people that, they're unstable when they're young and they're unstable when they're old. It's kind of like people that way. And so they vary in brightness. Now there's a number of classes of these things, but the ones that we care about are Cepheid variables. They're named for Delta Cephei. Delta Cephei is a double star in Cepheus. A really neat double, by the way. But it is it was the first Cepheid variable, and we know that because of the shark fin pattern of the variation in the light. It gets bright in a hurry and then it drops off, and then it gets bright in a hurry and then drops off. It's called the shark fin pattern. So Henrietta Leavitt discovered that there's this correlation between the period, how long it takes to go through one of these cycles, and its luminosity. Luminosity is the wattage on the light bulb. And so she was able to determine that there's this relationship here. And so if you can measure the period of a Cepheid variable, you know what its luminosity is. You're reading the wattage on the light bulb, you can calculate the distance. You have what's called a standard candle. And so Hubble determined the distance to the Andromeda galaxy by using a Cepheid variable that he found there. And he determined it was 1.4 million light years away. Now, he was off by almost a factor of 2, but really pretty good for the 1920s, okay? But that proved that these smudges were outside the size of the Milky Way. We had a pretty decent idea of how big the Milky Way was. And these things were way outside. This wasn't even close, okay? So it wasn't like it was marginal, they're a long way off. And so it's since been updated at 2.4 million years. Now, Edwin Hubble was measuring the distances to the galaxies, and Vesto Slipher was taking spectra and looking at the redshift. And I'll talk about what the redshift means here in a minute. Hubble interpreted these redshifts as Doppler shifts, and therefore a measure of recession speed. And so he was able to correlate his distances with these redshifts. Now let me talk about the redshifts for a minute. This is a Doppler shift. When a light is moving towards you, the waves get scrunched together and shorter wavelengths are blue, so we call that a blue shift. When something's moving away from you, the light gets stretched out, longer wavelengths are red, so we call that a red shift. And we can measure that difference in wavelength, delta lambda. Okay, and you can calculate a speed. Delta lambda divided by lambda, whatever wavelength you're looking at, times the speed of light gives you the speed. Some of you may have had a very uncomfortable encounter with the Doppler effect. That's how police radars work. Okay? So, Edwin Hubble was able to correlate these speeds with distances. And he found that, oh my goodness, everything's kind of matching up. They fall on this nice line here. And so it's called the Hubble law. There's the formula for it. It's a straight line formula if you're with the first axis at 0 here. And so H naught is called the Hubble constant. And it's got H naught because that's what the Hubble constant is right now. And as you'll see, it's been changing over time. So you can actually solve for the distance to a galaxy, take the Hubble constant divided by the velocity, and bingo, we got it. We got how far it is. Now that's okay, but the galaxies, that just measures the expansion of the universe. In fact, that graph, the only way you can conclude it is that the universe is expanding. That was a big deal, okay? Because there were arguments on the steady state, so I won't go through those, okay? The only conclusion you can make is that the universe is expanding. So how it really happened though, and when you get into some of the, get into the history of things, you find out that some people got credit for stuff that maybe they shouldn't have gotten credit for, okay? Because before Edwin Hubble did all his work, Carl Wilhelm and Wirtz had in 1922 and 24 deduced from their own data that galaxies that were further away had a stronger redshift. Okay, now they didn't have absolute numbers for it. And that's kind of where Hubble came in, and that's why he got the credit for it. But in 1927, which was 2 years before Hubble did all his stuff, George Lemaitre he was the first one to actually publish things deriving what is known as the Hubble law. So Hubble got credit for it. I'm guessing it was because maybe the U.S. was kind of dominating things at the time, and he was, these people were from Europe, and so we had to make some, I won't get into it. Okay? So Hubble actually was able to calculate how fast the universe was expanding, this sort of thing. So even though these Cepheid variables are very, very luminous, by the way, these things are unbelievably bright, 100,000 times more luminous than the sun, so you can see them a long way away. They're still limited to about 100 million light years. Now it gets us a lot of galaxies, but it doesn't get us, 13 billion years back. So the Hubble law works much better for distance galaxies. One of the problems with it, though, is these galaxies, particularly in clusters, are kind of orbiting around each other. So when you measure these things, when you're measuring the redshift, the data is somewhat corrupted by what they call the peculiar motion of the galaxies. So, and you can't really do it for nearby galaxies because the actual, like, Andromeda is moving towards us, okay? So that peculiar motion of the galaxies is much more pronounced. It's less pronounced or less affected by on the data when you move further out. That helps you. Well, one of the things that happens here is that the intrinsic speed of the galaxies gets pretty big when you get out quite a ways. And so the results can get distorted unless you use relativity to correct for some of this stuff. Also, it varies with time. The universe was, we thought was expanding much more quickly in the past and is slowing down. And we'll get to that. Okay? So that's why the H0 means that's what we're measuring today. And you also have to take into account the fact that as these numbers, get bigger, where you can have delta lambda approaching lambda, you get 1, and that would tell you that the galaxy's moving at the speed of light, okay? Which it isn't. So you've got to take into account special relativity. And that's why this graph comes out like the way it does. It's not a nice linear thing. In fact, when you get up here, it's really tough to get a good distance. The other ones that we can use are our Lyra variables. They live in a little spot right here. So if you can find an RR Lyra variable, you know pretty much what its luminosity is. You don't have to measure the period or anything else. You know what the luminosity is because they're all clustered in this one spot. And they have a very specific light curve so you can identify them. And so you can use, in fact, that's what Heber Curtis used to look at the globular clusters around the Milky Way galaxy to, number one, figure out where the center of the galaxy is, and also, number two, to figure out how big the Milky Way is. He was using our Lyra variables. And so that's what he did. These are his locations for distances, and there's the center, and you can see that they're all kind of clustered around the center in space. Okay. This is probably a relationship that most of you may or may not have heard of, but it's extremely popular among galactic astronomers, and that's the Tully-Fisher relationship. And it uses the relationship between the mass of a spiral galaxy and its rotational velocity. And so if we can measure the rotational velocity of a galaxy, we know what its mass is. And if we know what its mass is, we know how bright it is, how luminous it is. And so we can measure that luminosity and measure the brightness and get a distance. Okay, so this is the other thing that was first published in 1977. So that's how you do this. And so the mass, again, correlates with the luminosity, so we can figure out the distance. And so what they do is they use a long slit spectrograph. And you can measure this width, and that width has to do with the rotational speed. Okay, this offset actually. So this part is moving towards you, this is moving away from you. I'm assuming this is the blue side and this is the red side, but could be wrong. But anyway, if you measure that offset, you know what the difference in rotational speed is because of the Doppler shift. That difference in rotational speed gives you the mass of the galaxy, and from the mass of the galaxy, you can figure out the luminosity. And then from that, you can figure out the distance. I make it all sound so simple, right?
But how does that work when you're not looking dead on? Across the
No,
plane?
as long as you've got some sort of an angle, you can actually calculate that. Okay, this one here is, this is the prime example where you're edge on. But if you're face on, you can't do it. But if you've got pretty much any kind of an angle, you can take that into account. So it's really been extensively, refined and studied. So it's great for the large scale measurements of the universe and cosmological studies. This is a pretty easy number to get with, you don't have to wait for a supernova to go off in a particular galaxy. So this is also independent of the Hubble constant. It takes care of the fact that the galaxy might be moving towards or away from you because it's rotating around the other galaxies in the cluster. It's called the peculiar motion. And so this cancels that out, which is one of the things that sort of corrupts the Hubble constant.
Gary?
So this is how it works out, where you've got the rotational velocity and luminosity.
Could you bend the microphone up? It's rubbing on you.
Oh, okay, sorry about that.
Thank you.
Okay. So that's how it works. The other way we get distances to galaxies is through type 1A supernova. And this turned out to be really interesting, okay? What happens in all you've seen is double stars, right? And if you have one star go through its life cycle and is sitting there as a white dwarf, if the star next to it swells up to be a red giant, it can dump material onto that white dwarf. White dwarf is generally degenerate carbon. And if you dump enough material on it, you get to something called the Chandrasekhar limit, at which point the pressures and the pressures are so high inside that dwarf star because of all the material that's piled up on it that the carbon ignites and the darn thing explodes very, very quickly. And we understand the physics of that very, very well, and so we know what those luminosities are. And they're great. One of these things goes off about once every 100 years in every galaxy. So when you're looking at billions of galaxies out there, these things are popping off all the time. And they're bright enough you can see them all the way across the universe. So, yeah, you get to about 1.44 solar masses. That's when the thing pops off. It's called a type 1A. Has a very specific pattern to it. So, the fact that they're real consistent in this luminosity, we can use them. And see, if you look at, how we, you can tell these things, follow this curve amazingly well. So they're great standard candles, particularly for distances. So in the late 1900s, we wanted to find out how much the universe is slowing down. Because with gravity, this thing should be slowing down. And if it's slowing down at a particular rate, it's going to stop, turn around, and come crashing back into a big crunch. If it's past what's called the escape velocity, then the thing is just going to expand on forever. And so there was a group of scientists that were using type 1A supernova to try to measure this slowdown, and in 1998 they had an oops. Okay, what they actually found out is that the universe is speeding up. It's not slowing down. And so we've given that, we don't know why it's doing that, by the way, We've given it the term dark energy, just because we're real creative at this stuff, okay, at naming things. So it's dark energy, but we don't know what's causing it. In fact, if you're not doing anything this week, just go ahead and, if you figure it out, you get a free trip to Stockholm and $1 million prize, okay? This has got, a lot of people have tried. So it seems it's expanding, and it's been confirmed a number of times. And that's why in 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize for that work. Okay, so we still don't know what's happening there, but that keeps these theoretical astronomers in business, I guess. Okay, gives them their grants, everything else. So the other way we can do this, and this is another one of those real esoteric ones, is you look at the velocity dispersion in a cluster of galaxies. And it's basically how quickly these things are orbiting around each other. And by measuring that, we can get some idea of the mass and the halo of the dark matter around it. And so that also correlates to the size of the galaxy cluster. So if we can correlate those, we can figure out how big this galaxy cluster is, and if you measure the size, you can calculate the distance. If you measure the angular size of this thing, and if you know how many millions of light years it is across, then you can calculate the distance, and that's another way that we do it. So this is kind of the whole thing, kind of wrapped up. You got parallax, you got spectroscopic parallax, you got population 2 RRI variables, population 1 Cepheid variables. I won't go through population 1, population 2, and then type 1a supernovas and the Tully Fisher constants. So it's cool stuff, but it ain't easy, okay? I mean, it sounds easy sometimes. I don't know, did I make it sound easy? I don't know. And I'd be happy to try to entertain any questions anybody might have. Oh, wow. Let's start in the back.
Where does the 186,000 pound light year, where does that fit into this whole thing?
The what?
186,000 light years, how does that fit into the skyscraper?
186,000 light years, what?
A light year, how does that fit into?
Oh, okay, yeah. A light year is the distance how far something light travels in 1 year. So if you take 186,000 miles per second, multiply it by 60 seconds, by 60 minutes, 24 hours, 365 days, gives you about 6 trillion light years. And that's a big yardstick. Not so good for measuring things around the solar system. That's what we use to measure distances to the stars and to galaxies, along with parsecs. One nice thing about using light years, you're looking back in history. And so if you look at M13, for example, is 25,000 light years away. You're seeing it as it was 25,000 years ago. And that's always kind of neat to tell people that, okay? They get an appreciation for it. And then what I tell my philosophy students is, here's a good philosophy problem for you. Everything you see as it was. You never see anything as it is. Okay? You're seeing me as I was about 50 nanoseconds ago, not as what I am right now. Okay? So everything you see in the past. So, I kind of turn them loose on that and say, okay, have fun.
Really?
Have fun with it. So, did that answer your question, I hope? Light year, by the way, is way too big to measure distances around the solar system. Solar system is about 8 light hours across. Okay? I saw another hand up over here, yeah.
When the first book on Cepheid variables were to figure out that there was a correlation between the period and luminosity.
Yeah?
Was that done on Cepheids in the Milky Way?
No, that was done by observing the large Magellanic clouds. And at the time, she was one of the Harvard computers. And at the time, Harvard had a telescope in Chile. And so they would send these plates back, and then she would analyze them. And so this is unbelievable. I mean, I'm going, salute here, because this is unbelievably tedious work. You got to look at a plate, literally thousands of stars, You got to figure out what the brightness of each one is. You have to document that. And then you have to look at a plate that was taken 2 days later, figure out the same thing for each one of them, and do that plate after plate after plate.
So the assumption was they were all the same distance.
Yeah.
Down and ground up.
Mhm.
That's what these are.
Yeah, they were all the same distance. In fact, that's why we really like clusters of stars. Clusters of stars are amazingly handy because number one, they're all about the same distance, which takes that variable out of it. They were all basically made from the same gas cloud, so their composition is essentially the same. And they're all about the same age, give or take 1,000,000 years. Okay? Now, it may seem like a lot, but when stars are lifetime expectancies are on the order of billions of years, 1,000,000 years is not a whole lot. Yes?
I don't know that I'm going to lean on your expertise.
Oh, shoot.
Inform my question. There was a physicist some years back, I believe, who published a paper trying to counter this idea of the increasing rate of expansion through some sort of errors speculated in centrifugal acceleration. Are you coming up with a paper?
I'm not familiar with that at all.
I was trying to look for that. I'm sorry, that's
Yeah,
probably going to be
that's
key to
all
my
right.
question then, because I was just trying to get an idea. I mean, the idea of the universe expanding at an increasing rate is really probably the most mind-boggling aspect of our recent studies, as I understand it.
And it's been confirmed. When it first came out, I thought, there's got to be some errors in here someplace, but it's been confirmed by a number of other observations.
So let me see if I can track down the
Okay.
particular author that I'm trying to come up with, and maybe that will help.
Okay. By the way, you said you wanted to rely on my expertise. You know what the definition of an expert is, don't you? The X is for a has-been and a spurt is a drip under pressure. Okay.
Say it again, you didn't get it.
I said the X is for a has-been and a spurt is a drip under pressure.
You mentioned that there were these women computers.
Yes.
How were they found and how many were doing this?
He hired about 80 of them over the period of about 40 years. This was Edward Pickering at the Harvard Observatory. Okay, I can't give you the whole 1 hour lecture on this, but I'll give you the Cliff's Notes version. In the late 1800s, dry plate photography came into being. And so that said we could take things, take photographs of things at the telescope and bring them into a lab for later analysis. The other thing that happened is we also finally understood the spectrum. We knew these spectrum lines were there, but we had no idea what they meant. And it was the late 1800s where we went, oh, that's what they mean. And so Harvard Observatory started taking spectrum of stars. It was objective prism spectroscopy, which I won't, but anyway, you get a whole bunch of spectrum on one sheet. And Edward Pickering needed people to analyze this. And it was very, very tedious work. And he couldn't find people to do it, and suddenly he realized that there was a lot of women out there that had degrees in physics, mathematics, in the sciences that weren't employed in the sciences. So they employed them at Harvard. And what came out of that was absolutely phenomenal, because they were working on the cutting edge of astronomy. That was the cutting edge at the time. And so Henrietta Leavitt was one of them. And of course, she was actually, they wanted to nominate her in 1926. They wanted to nominate her for a Nobel Prize for her work. And when they did the research, they found out that she had passed away in 1922, and they don't award it posthumously. So she would have been a good candidate. Edward Hubble was one really, cheering her on. But the star classifications that we use, OBFJKM, that was done by, oh God, I can see the picture. Anti-jump cannon did that. They made a bunch of discoveries, and that's why I titled the lecture, The Women That Launched 20th Century Astronomy. It's a good book written by, I think her name is Coble, called The Glass Universe. So if you're really interested in it, look that one up. It's a fascinating story. It really, really is. I think it's really cool.
So for things like the distant stars that you need light years to calculate, how did they know the speed of light without modern equipment?
First one was done by Romer, but he didn't have a good number for the Earth's orbit. But if you look at Jupiter and you look at the planets or the transit of the moons, you find out that when we're on the far side, the sun is here and Jupiter is over here, they're a little slow. And when we're here, they're a little fast from what would be predicted. And that difference is the time it takes light to go across the Earth's orbit. So that was some of the earlier ones. So.
Picnic we had a discussion about the differences between a type 1A supernova and a nova. And they're both basically working on the same mechanism where you have a red giant that's accreting onto the white dwarf, but one ends up in an explosion, supernova explosion, the other one ends up in just a brightening without any damage to the stars.
Yeah,
So-
to the best of my knowledge, it has to do with the
Gary,
rate of the
could you
deposition.
repeat the question? Not everybody can hear.
Oh, okay. It's the difference between type 1A new supernova and type 1 supernova. Okay, there are other supernova, by the way. You get, Betelgeuse, for example, is a red giant. It's massive enough, and when the
Type 1A supernova and a nova.
okay,
Just a
well,
nova, that's a brightening, but the star itself isn't destroyed.
okay, a whole different process then.
But
Okay.
aren't they both basically the same mechanism where you're accreting material from the red giant star onto the white dwarf?
No. No, I don't think so. I gotta be careful on that because I'm not exactly familiar. But if you look at supernova, there are other types of supernova.
Yes.
Large stars, when iron accumulates in the core, that's the end of the road for them. And then because of that, they collapse quickly, and then the rebound is the star part. Whole nother lecture. Okay, a couple more. Yeah.
I just have like a very naive question.
Yeah, no such thing as a naive
When
question.
observation takers take observations for such a huge distance, how do they plan, like when there's like no obstacles in between? So like they're clearly trying to measure something like way far away.
Right.
But you cannot ignore the fact that there have to be obstacles in the way that they can't see past. Like, so I've often wondered, like, okay, you take an observation, how do you know what you're looking at is like the thing you started from, like, started looking at?
Oh, we know where these things are very accurately in the sky. Okay, so we can go find them, and so we know where they're at.
Oh, yeah.
Now, you want to make sure, obviously, that the moon's not passing in front of it
Right, yeah.
or whatever, okay? But that's all predictable.
Okay.
That's all very, very predictable.
How come you can't measure the Tully Fisher straight? Like off an angle?
If the galaxy is flat on and it's rotating, you don't, the stars aren't moving towards or away from you, so you don't have a Doppler shift. The Doppler shift measures things that are moving towards and away from you. If it's at a little bit of an angle, then some of them are moving towards you and some of them are away from you. So that's why we can't measure it flat on. We can't get a good number for it. Now, you could try and time the stars going around, but that takes millions of years, and most of us don't have that patience. Okay, gang, I thank you very much. I hope you learned something, and I hope I didn't confuse the